To determine when the National Electrical Code NEC Section 230.95 requirement for ground fault protection for services was introduced, you can use several methods. Firstly, review historical NEC codes. Obtain copies of the NEC codes from 1971, 1975, and onward. These are key years to examine. Check the NEC Section 230.95 in each code edition to pinpoint when the requirement for ground fault protection for services was first included. Secondly, contact a code development organization. Reach out to the National Fire Protection Association, NFPA, which oversees the NEC. You can contact them by email or by telephone at 225.766-200. Explain that you need to know the specific date the NEC Section 230.95 requirement for ground fault protection for services was added to the code. Thirdly, consult code interpreters. Contact organizations such as the International Association of Electrical Inspectors (IE) or the Electrical Safety Foundation International (ESFI) for guidance. These organizations have experts who can provide interpretations of code requirements. They can help you determine if a specific electrical service met the code requirements in effect at the time it was installed. NEC codes are typically updated every 3 years. The NEC Section 230.95 requirement for ground fault protection for services was likely introduced in either the 1971 or 1975 NEC edition. If a service was installed in 1973 and does not have ground fault protection, it may not have met the code requirements at the time of installation, so be sure to review the exact code in place in that year. Ground fault protection of equipment is intended to provide protection from line to ground faults, but is not intended to clear phase to phase or phase to neutral faults. For effective ground fault protection, coordination with the overcurrent protective devices must be achieved. Ground fault protection is required for each service disconnecting means rated 1000 amps or more and installed on solidly grounded wire electrical systems with more than 150 volts to ground, but not exceeding 600 volts phase to phase. The maximum setting of the ground fault protection shall be 1200 amps. The intent is to provide ground fault protection to reduce the likelihood of destructive arcing faults that could occur within the service equipment. A common misconception is that ground fault protection will provide personnel protection, but that is not the purpose. Personnel protection is provided by ground fault circuit interrupters. There are exceptions to the requirement of ground fault protection for services. The first exception states that ground fault protection of equipment is not required on services for a continuous industrial process where a non-orderly shutdown will introduce additional or increased hazards. The second exception states that ground fault protection of equipment is not required on fire pumps. To locate historical NEC codes, firstly check with local libraries. Many public and university libraries keep archives of older codes. Secondly, contact electrical trade organizations. Organizations like the IE often have historical documents available. Thirdly, search online databases. Websites dedicated to historical documents may contain scanned versions of older NEC editions. When reviewing historical NEC codes, pay close attention to the effective dates of each edition. The NEC is updated every 3 years, but local jurisdictions may adopt the new code later. Ensure you are looking at the code edition that was in effect at the time of the installation in question. Ground fault protection functions by monitoring the current balance in a 3-phase system. In a balanced system, the current flowing through each phase conductor should sum to 0 at any given point. A ground fault occurs when current leaks to ground, creating an imbalance. The ground fault protection system detects this imbalance and trips the service disconnecting means. The components of a ground fault protection system typically include current transformers, a ground fault relay, and a tripping mechanism for the service disconnecting means. The current transformers are installed around the service conductors to measure the current in each phase. The ground fault relay monitors the output of the current transformers and detects any imbalance. If the imbalance exceeds a predetermined threshold, the relay sends a signal to trip the service disconnecting means, interrupting the power supply. When assessing whether a 1973 installation met the code, consider the specific requirements for overcurrent protection in place at that time. Overcurrent protection is designed to protect conductors and equipment from excessive current that could cause overheating or damage. The NEC specifies the types and sizes of overcurrent devices, such as fuses and circuit breakers, that are required for different applications. These requirements are based on the ampacity of the conductors and the characteristics of the equipment being protected. If the 1973 installation lacked ground fault protection and it was determined to be required by a code in effect at that time, it would be necessary to upgrade the service to comply with current standards. This could involve installing a ground fault protection system or replacing the service equipment altogether. Before making any changes, it is essential to consult with a qualified electrical engineer or inspector to ensure that the upgrade is performed safely and in accordance with all applicable codes and regulations. Ground fault protection is intended to reduce the risk of electrical fires and equipment damage caused by ground faults. Ground faults can occur when insulation fails or conductors come into contact with grounded surfaces. By detecting and interrupting ground faults, ground fault protection can prevent these faults from escalating into more serious hazards. Additionally, properly installed and maintained ground fault protection can improve the reliability of the electrical system and reduce downtime due to electrical failures. When evaluating an existing electrical service for code compliance, it is important to consider the entire system, not just the ground fault protection. This includes the service entrance conductors, the service disconnecting means, the grounding system, and all other components of the service. Each of these components must be properly sized, installed, and maintained to ensure the safety and reliability of the electrical system. If any deficiencies are found, they should be corrected promptly to prevent potential hazards. Furthermore, be aware of the specific interpretations and amendments to the NEC that may have been adopted by the local jurisdiction at the time of the 1973 installation. Local amendments can vary from the national code and may have influenced the requirements for ground fault protection in that area. Contacting the local electrical inspector's office can provide clarification on any local amendments that were in effect at that time. In addition to reviewing the NEC and consulting with experts, consider examining any available documentation related to the original installation. This documentation may include electrical drawings, specifications, and inspection reports. These documents can provide valuable information about the design and construction of the service and may shed light on whether ground fault protection was originally intended to be included. If documentation is unavailable, it may be necessary to perform a thorough inspection of the service to determine its configuration and condition. This inspection should be performed by a qualified electrician or electrical engineer who is familiar with the NEC and other applicable codes and standards. Remember to document all findings and recommendations in a written report. The report should include a detailed description of the service, an assessment of its compliance with applicable codes and standards, and recommendations for any necessary repairs or upgrades. This report can be used as a basis for making informed decisions about the service and ensuring that it is safe and reliable. In summary, determining whether a 1973 electrical service met the code requirements for ground fault protection involves researching historical NEC codes, consulting with experts, and examining any available documentation. By following these steps, you can gain a clear understanding of the requirements that were in effect at the time of the installation and ensure that the service is safe and compliant with current standards. The NEC is not retroactive unless specifically stated within the code. This means that an electrical installation that was compliant with the code at the time of installation is not required to be upgraded to meet current code requirements unless the installation is altered or expanded. However, it is always recommended to upgrade electrical systems to meet current code requirements whenever possible to improve safety and reliability. Also remember that a thorough understanding of electrical systems is essential for making informed decisions about the safety and compliance of electrical installations. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical professional before making any changes to an electrical system. Consider the long-term implications of any electrical upgrades or repairs. Upgrading to meet current code requirements can not only improve safety, but also increase the value and longevity of the electrical system. Regular inspections and maintenance can help to identify potential problems early and prevent costly repairs down the road. And finally, familiarize yourself with the local permitting requirements for electrical work. Many jurisdictions require permits for electrical installations and upgrades. Obtaining the necessary permits ensures that the work is inspected and complies with all applicable codes and standards. It is essential to understand the role of each component in the ground fault protection system to properly troubleshoot and maintain it. The current transformers, also known as ground fault sensors, are responsible for measuring the current in each phase conductor. These transformers produce a secondary current that is proportional to the primary current flowing through the conductor. The ground fault relay monitors the secondary currents from the current transformers and detects any imbalance. The relay is typically a solid-state device that is programmed to trip the service disconnecting means when the imbalance exceeds a predetermined threshold. The tripping mechanism for the service disconnecting means can be a shunt trip or an undervoltage release. A shunt trip is a solenoid-operated device that trips the circuit breaker when energized. An undervoltage release trips the circuit breaker when the voltage drops below a certain level. Both types of tripping mechanisms are designed to quickly interrupt the power supply in the event of a ground fault. Regular testing and maintenance of the ground fault protection system are essential to ensure its proper operation. Testing should be performed in accordance with the manufacturer's recommendations and applicable standards. Maintenance should include visual inspection of the components, cleaning of the contacts, and verification of the settings. If any problems are found, they should be corrected promptly to prevent potential hazards. In addition to ground fault protection, other types of protective devices are commonly used in electrical systems to protect against various types of faults and overloads. These devices include fuses, circuit breakers, and surge protective devices. Fuses are overcurrent protective devices that contain a fusible link that melts and interrupts the circuit when the current exceeds a predetermined level. Circuit breakers are electromechanical devices that automatically interrupt the circuit when an overcurrent or fault condition is detected. Surge protective devices are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. Each type of protective device has its own characteristics and applications. It is important to select the appropriate protective devices for each application to ensure the safety and reliability of the electrical system. Furthermore, be mindful of the specific requirements for selective coordination of overcurrent protective devices. Selective coordination means that only the overcurrent device closest to the fault should trip, minimizing the impact on the rest of the electrical system. Selective coordination is particularly important in critical applications such as hospitals and data centers, where loss of power could have serious consequences. The NEC provides detailed requirements for selective coordination of overcurrent protective devices. These requirements must be followed to ensure that the electrical system is properly protected and that downtime is minimized. Keep in mind that electrical codes and standards are constantly evolving to keep pace with new technologies and safety concerns. It is important to stay up to date on the latest changes to the NEC and other applicable codes and standards. This can be accomplished by attending training courses, reading industry publications, and participating in professional organizations. By staying informed, you can ensure that your electrical work is always performed safely and in compliance with the latest requirements. When dealing with electrical installations, safety should always be the top priority. Electrical work can be dangerous, and even a small mistake can have serious consequences. Always follow safe work practices and use appropriate personal protective equipment when working on or near electrical equipment. This includes wearing safety glasses, gloves, and insulated tools. Never work on energized equipment unless it is absolutely necessary, and always de-energize the equipment and verify that it is de-energized before starting work. By following these safety precautions, you can minimize the risk of electrical shock, burns, and other injuries.